Okay, so I'm going to do this using dimension analysis, and the idea is you still have to think about what's going on. You have to think where you're going in the process as you do this problem. Sometimes in dimensional analysis, you just look for patterns and hook things up here and there. Make sure that the right things are crossed out. That's one of the reasons I'm not really a fond of dimensional analysis. But let's see what we can do with it. So first of all, let's look at the problem. It says how many grams of solid iron 3 hydroxide will precipitate when 100 mils of 0.3 molar sodium hydroxide, which is an aqueous solution, is added to an aqueous solution of 200 mils of 0.25 molar iron 3 nitrate. Okay, so what you have to understand what's going on here. Okay, so you're taking, another way to look at it is you're going to take 100 mils of 0.3 molar sodium hydroxide. So you can think of that as so I have one container that's 100 mils, okay, 0.3 molar sodium hydroxide, okay? And then I have another container that's 200 mils of 0.25 molar, all right? And what I'm going to do is I'm going to mix them together, and there'll be these two chemicals will come together, and they're going to form a precipitate, and that precipitate is going to be this is solid iron hydroxide. Okay, so we're going to write the chemical equation. So let's write the word equation, and then and from that come up with the balanced chemical equation. So what we're doing is we're taking aqueous sodium hydroxide and adding it to aqueous iron 3 nitrate. So this is a double replacement reactions where you're taking two ionic compounds, combining them. So what you're going to do is you're going to be swapping. So the sodium is going to combine with the nitrate, and the iron is going to combine with the hydroxide. And so you're going to form sodium nitrate and iron 3 hydroxide. And I told you this is a solid, okay? Right, so that's it. So now I can write the word equation is aqueous sodium hydroxide plus aqueous iron 3 nitrate yields sodium nitrate. I don't have to worry about the state. I don't tell you that. Plus solid iron 3 hydroxide. Can't spell here. It's not spelled right. It's not soiled, but it's solid. Okay, so next thing we're going to do is we're going to change this to okay, so here's our four substances. Sodium hydroxide is Na plus, OH minus. They have the same charge, so no subscripts. Iron 3 nitrate, iron is 3 plus, nitrate is 1 minus, so you need to have, so swap, so you crisscross charges, put a 3 and a 1 here, and you can leave the 1 off. Sodium nitrate is Na plus, nitrate is NO3 minus, so they have the same charge again, so you don't have to put anything in subscripts. And iron 3 hydroxide is Fe3 plus, OH minus, only one charge, so you can crisscross. And you got 3 over here and a 1 over here. All right, now put those in the equations. So sodium hydroxide, iron 3 nitrate yields sodium nitrate and iron hydroxide. Okay, next thing with the balanced equations, and I say start out with the substance that has the most subscripts, and it's actually this. You can either start out with this guy or this guy. So I'll start here. So I have 3 nitrates. So I have to come over here and put a 3. Okay, so I have 3 nitrates, and now I have 3 sodium, so I'm going to come over here and put a 3. Okay, and notice I have 3 OHs now. I'll go over here, and it's fixed, and I have my balanced equation. Okay, now we're going to use this chemical equation to come up with our answer. Okay, so now we're going to apply dimension analysis. Okay, so you need to have the balanced equation. And to do dimension analysis using chemical equations, you need to use what is called mole ratios. And actually there's 6 mole ratios. You have 3 NaOHs for every one of these. You have 3 NOHs for every 3 of these. Okay, and I write them down here. So we have 3 to 1 right here and here. Then I have 3 to 3 here. Then I have 3 to 1 here, here. And then I have 1 to 3. And then I have a 1 to 1. And then I have a 3 to 1. Now, you don't have to write them all out if you know which ones you're going to use, but I wrote them all out. The other thing about dimensional analysis, these can be called conversion factors for molar ratios, is that you can write them two ways. You can write them this way, or you can write them in the reciprocal form like this. And the reason why you can do that is when you do the cross out, you're going to want to cross out, make sure that opposite sides cross out. Okay. Okay, so we'll keep this list available to us for the next step. Okay, so no matter what you do, you always need to find out how many moles of substance you have, because that's what the chemical equation is in. So depending on the state you have, you'll use different types of conversions. If you have a solid, you'll be using molar mass. If you're using gases, you'll be using the ideal gas law, PV equals nRT. If you're given a pure liquid, you'll be using density and molar mass. And if you're using aqueous solutions like we are here, you will be using molarity, okay, which is given in the problem. Okay, so the problems give you the volume, and they give us the molarity. Okay, all right. So what we're going to do is we're going to do a dimensional analysis. So we have the liters of sodium hydroxide solution, and this is the molarity. Molarity is written as 0.3 mole big M. Okay, NaOH. What that stands for is 0.3 moles of NaOH per liter of NaOH solution. Okay, so if we had moles, so we have liters here, so we're going to use the mole, write molarity as moles over liters. Now, if this was moles, we would flip it upside down. All right, so what we're going to do is we set it up. So what we get is this cancels out with this, and then we end up with 0.03 moles of sodium hydroxide. So that means that in 0.1 liters of 0.3 molar sodium hydroxide, there are 0.03 moles. Now, remember what I did here. I changed the 100 mils to 0.1 liters. Okay. Divided by 1,000. So I could have done that. That also is part of the dimensional analysis. You could have written 100 mils, okay, times 1 liter over 1,000 mils. Okay, and then the mils would cancel out, and you get 0.1. That's the way you can do it. Okay. Okay. So how many moles of iron 3 nitrate do we have? We have 0.2 liters of the solution. The concentration is 0.25 moles per liter. Okay, the liters will cancel out, and you end up with moles of iron nitrate. Okay, so this is how much reactant we have. What we have of. So we have the two reactants, so we know how much of each. The problem is this. Are they in the right ratio? Are we going to, if I use 0.03, will it use up all of the 0.05? Or is it going to be, if I use the 0.03, will some of this be left over, or the other way around? So what we're going to do is we're going to try to find out what is the proper amount of each we need. And so this is called limiting. Okay, so now we're going to find the limiting reactant. Since we have 2 more than one of the reactants, you have to find out. Maybe they're both in the right amounts, but more than likely one of them is going to be limiting. So we're going to use the mole ratios, and we're going to use the moles that we came up with. So what we're going to do is that if I have 0.03 moles of sodium hydroxide, how many moles of iron nitrate will I need? So I have this amount, and I want to know how much of this I will need, okay? All right, so what I'm going to do is so I have 0.03 moles of NaOH. The molar ratio is this, okay, and I got that from the molar ratios. I flipped this, the flipped version of it. So I will cancel out the moles of sodium hydroxide, and I get 0.01 moles of iron nitrate. Okay, so what this means is to use the 0.03, I only need 0.01, all right? And I have 0.05, so you can see that this is going to be in excess, okay? So you really don't need to go to the next step, right? Because we know we have more than enough of the iron nitrate to use up all of the sodium hydroxide. So this is going to be our limiting, okay? But let's do the reverse and figure out. Now what we're going to do is that if I have 0.05 moles of iron nitrate, how many moles of sodium hydroxide? Well, we're going to do the same thing. We're going to use the molar ratio. This time we're going to flip it, okay? So it's 0.05. This comes, so if you went back a couple slides ago, you see it. So we have 0.05 moles of iron nitrate. Here's the molar ratio. So that cancels out with this. And then we end up 0.15 moles of sodium hydroxide. So to use up all the 0.05 moles, I need 0.15. And notice I only have 0.03. So I don't have enough of the sodium hydroxide to use up all the 0.05. So that tells me, just like up here, is that the iron nitrate is excess and the sodium hydroxide is limiting. Okay, so think about this, okay? Let's think about what happens here. So in the first case, we found out if I have a certain amount of sodium hydroxide, how many iron nitrates has, okay? And I find out I have more than enough. I need 0.01 and I have 0.05, all right? Okay, so that's one way to find out the limiting. So I find out the excess, okay? Or you can do it, do it this way, or you can check it out this way. If you have 0.5 moles of iron nitrate, how many moles of sodium hydroxide, and I find I need 0.15 moles, which is not enough to use all the 0.05. So this gives me the limiting. So it doesn't matter which one you use. Actually, if you do both of them, that's good, but it has to make sense. All right, so my limiting is going to be the sodium hydroxide. So I'm going to use the 0.03 moles of the sodium hydroxide to figure out my product. Okay, I'm not going to be using the iron nitrate. Okay, because we're not going to be using it all up. We're going to be using all this up right here. All right. Okay, finally I'm going to find the molar product. So the molar product, product is FeNO3, and it's a solid, so we're going to be using molar mass. We're going to need to use the molar ratio. So the molar ratio from up above is, we're looking at the ratio of the sodium hydroxide, the reactant with the product. Okay, and the molar mass of iron hydroxide is this. Okay, so so this is what we started out with, and we're going to multiply that by the molar ratio. When you do that, the moles of sodium hydroxide cancel out, and then you multiply it by the molar mass, and moles of iron hydroxide cancel out with, and then you do the math. 0.01 times 1 divided by 3 times 106.87 and you end up with grams of iron hydroxide or 3.56 grams of sodium hydroxide. Okay, so this is the idea, is that here's what I want you to do. So that was number one of the test problems. I want you to do this version, this problem here, which is quite a bit like the problems just had, and solve it. Okay. And I'll do I'll start setting up the next couples and see how that works out for you. Okay. All right. So do this problem for me, and then hopefully it works out for you. Make sure you get the balanced equation. Okay. So what you're doing, you're adding silver nitrate with sodium chloride. Okay. So what is the product's going to be, and balance that equation. Remember, this is going to be a double replacement reaction. Okay.